Okay, so we're now moving on to the composition structure of the atmosphere. Uh, in other words, we're not taking a look at, for example, what's happening at one given location. We're looking at what does the atmosphere look like if I looked at it over the whole globe, or how might it change from one part of the globe to another. So that's what we're focusing on with this part right now. So there's some interesting things. The atmosphere is as fluid, and what impacts one area of the world actually can impact another. For example, this time of year, the Sahara Desert produces dust storms. You'd think, they're going to just stay over there and not going to bother anybody except the Saharas. Well, they actually move across the Atlantic Ocean. You can see an image here. When they move across, they keep hurricanes from forming. And they can provide low visibility, dust and all, the southeastern part of the United States and the Caribbean. There's been instances where visibility when these events have come across. And this is all dust that was formed over the Sahara Desert. So, weather can go from nice, simple, beautiful day outside to, it is in trouble. And it's very variable. So, let's take a look at the Earth. The Earth consists of four basic systems. Systems are mechanisms that work together to influence how the Earth as a whole works. We have the atmosphere is what you're going to study, the hydrosphere. Think about all the oceans, the lakes, the rivers. The geosphere, think about the rocks, volcanoes, and the biosphere is us, or plants. So, and if you look at the whole atmosphere, it's pretty daggone thin. Really, 99% of its mass is within 20 miles. Heck, if you ran a marathon, you'd run longer than the running up through the atmosphere. So, in the lower part of the atmosphere, most of it, basically, the atmosphere are all identical proportions. In other words, if I went up to the top of Mount Everest, 78% of that gas that makes up the atmosphere up there is going to be nitrogen. So, with that, oxygen makes up about almost 21%. It's the second most popular element. And basically, 1% is split between everything else. Carbon dioxide, dust, all kinds of junk. And the atmosphere does have aerosols in it. And those aerosols are things that come out of volcano eruptions, industry, agriculture. Just we talked about the Saharan dust layer, perfect example of aerosols. Water. The most you're ever going to find is maybe up to 4% of the atmospheric volume in the lowest 1 kilometer of the atmosphere. What makes our clouds and precipitation. We wouldn't be a very good atmosphere if we didn't have carbon dioxide. Yeah, we want our plants to grow, right? Trees can take off and all, provide us fruit and vegetables. We need carbon dioxide. So, carbon dioxide, water vapor, all of that work together to help keep our atmosphere warm enough so we can live. There are other parts. There are pollutions. And some of these are man-made. Some of them may happen from volcanoes, for example. There used to be a lot of smog around. It's gotten a lot better through the years, but still visibility. If you go up on top of some mountains in the Rockies, Rocky Mountain National Park, they actually have a chart up there showing from a given location. And they show you how, while we have improved overall in pollution, we're still limited by how far we can see due to aerosols in the earth. So it's interesting to know that. All right, when we study the atmosphere, we use what we call the scientific method. If you took any science class in high school, you probably have run across this. And the idea is we observe something. Say, for example, I observe that thunderstorms coming across the Appalachians into Virginia sometimes intensify, sometimes they die out. Actually, the same exact thing can be said in West Virginia. Some thunderstorms will intensify as they move across the Ohio River. Other times they will weaken. So the question became, why? Why does this happen? So we drew up an hypothesis. I actually did this experiment. Worked with North Carolina State University on it, as a matter of fact, for a couple people's math groups. And we tested that. And then we looked at the results. And we found, some of these ideas we had don't work. So let's draw up some other ideas. So we did. And eventually we wound up with one that, hey, this seems to verify pretty doggone well. So we said, it looks like it works. So with that in mind, we now have a better understanding of when thunderstorms are going to increase when they move across the West Virginia mountains, or when they're going to decrease when they move across the West Virginia mountains. So this is a very kind of thing we can apply to the atmosphere to learn about how to make a better weather forecast. We can also model the atmosphere. Some things, such as the Purdue's tornado vortex chamber, actually simulate what a tiny little tornado would look like. Very physical model. Numerical models. That's what I worked on in grad school, and I did some when I was in the weather service. All they are is mathematical equations representing all the variables in the atmosphere and how they're going to change. Unfortunately, we can't solve these equations. No mathematician, at least currently, knows how to mathematically solve the equations that govern all the variables of the atmosphere. So we approximate them. That is why you see errors in our forecast. One of the many reasons. How do we observe weather? We talked about it. We use ASOS. With co-op observers, radiosondes go up. Radiosonde replacement systems, dropsondes. Think about it. A radiosonde goes up in the atmosphere with a balloon. A dropsonde dropped out of an aircraft and goes down in the atmosphere. Many times dropsondes are employed in hurricanes. They can also be employed in nor'easters or strong low pressure systems sometimes. Sometimes even in thunderstorms, they'll fly over top very, very high up and drop some down. We've talked about remote sensing using radar, satellite. Here's a profile of the atmosphere. If you think about it, the troposphere temperature is always dropping. We live in the troposphere. Everything, if you climbed up all the way up Mount Everest, you're getting to the top of the troposphere. Now, if you're flying in a jet, you may fly in the stratosphere. But think about it. If you're living in the troposphere, so if you're climbing up a mountain, the temperature is going to get colder. If you get in the stratosphere, you're actually getting warmer temperatures. The temperature is warming with height. All right. Auroras are caused by the solar wind. So the more solar wind, the bigger the aurora is going to be. It's going to cover more of the Earth. That's why when you see these, oh, wow, that means it's a very strong solar wind. And here you can see the expansion that occurs with that. So these are just some of the things we wanted to talk about today with this atmosphere. So, and all it is sounding from northern Idaho. And I wanted to show you where the tropopause is and the stratosphere begins. Where the temperature begins to warm is actually the tropopause. And 150 millibars up. that aircraft in that area would be in the stratosphere. Now, this varies from location. It's actually higher in the tropics and lower towards the poles. But this is a very clear example of how the troposphere looks when we send a radio sonde. Well, I hope you got a little bit out of this, and let me know if you have any